So if X is binomial NP, we know that the PMF is probability X is equal to XK, whatever. I'm going to use K. N is K, P raised K, P raised N minus K. And the value of K from 0, 1, all the way up to N. Now we want to find the expectation of e raised xk. So we have to sum zero to n, and choose k, e raised kt, e raised k, q raised n minus k. Where do we go from here? Well, how about q raised n? Q raised n is a constant. Yes, I can pull that out, but that would just make things difficult on it. How about I do this instead? P e raised t raised k multiplied by q raised n minus k. Good. Well, where do we go from there? Q plus q squared. A, B, C, D, yes, that is correct. So I call that A, I call that B. Is that what you mentioned? Yeah. Okay. Fine. And then here you go. So I want to leave that part for a reason. So I'm going to go over here from there to here. That's the binomial theorem, right? Or the binomial formula. I can simply write that as P e raised t plus q raised n. Yes, a plus b raised n. That's the formula for that. Now, q is 1 minus p. So 1 plus p e raised t minus 1 raised n. I left this for a reason. Do you see some similarities between the moment generating function of a Bernoulli and the moment generating function of a binomial?
It's just going to the power of like trials.
It's to the power of n, right? This is Bernoulli and it's binomial. But why do we have this? That's the bigger question. And that will lead to a very important property. How do we go from a Bernoulli to a binomial?
binomial distribution, it's just a whole bunch of Bernoullis.
Right, it's a whole bunch of Bernoulli trials.
And Bernoulli trials.
And Bernoulli trials. Not only that, at any given time, the value of the random variable can be expressed as a blank of those Bernoullis. You can fill in the blank. Very good. Even before I do that blank. So if you recall, a binomial random variable is simply the sum of n iit Bernoulli p. You just add n of independent and identically distributed Bernoulli random variables, you end up getting a binomial. So I'm going to extend that idea to something very generic. Suppose x1, x2, dot, 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 all the way up to xn. The random variables. And let us define y to be the sum of those random variables. And also mxi of t is the MGF of xi. Yes. Now I want to find the MGF of the random variable y. Yes. Now, what is y? Y is the sum of those IID random variables. So expectation of e raised I equals 1 to n xi times t. Algebra. What I can rewrite that expression as a product. Do you agree with this? Correct. E raised x multiplied by e raised y is simply e raised x plus y. So properties of exponents, so that would become this. Since they are IID, one of the properties of expectation is that if the random variables are IID or independent, then I could pull the product up. So I can write it as I equals 1 to n expectation of e raised xi t. What is e raised expectation of e raised xi t? That is the moment generating function of the random variable xi. That's what we defined. Here is a question. Would it be wrong for me to go from here to them.
They're all the same.
So no or yes?
No, it would be wrong.
Yeah, okay. It would be wrong because they are IID. So pick one of the moment generating functions, they have to be the same because the MGF is unique to a distribution, and my case here is they are independent, identically distributed, so they all will have the same moment generating function, so raise n. If we go back to Bernoulli and binomial, a binomial is simply the sum of n independent, identically distributed Bernoulli P. I know the moment generating function of one of them. Yes, I am summing n of them. And what does the property tell us? Well, if you have a sum of IID random variables, the moment generating function of the sum is simply one of the moment generating functions raised to the power n. So moment generating functions make things easier, especially in terms of finding new distributions and things like that.